Forget black holes. Forget supernovas. Forget everything you think you know about the dangers of space. Because there is something out there that makes all of them look harmless. It is not a void. It is not dark energy. It is a star. A dead star. Only 12 miles across. That possesses a power so extreme. It can erase your DNA from half a solar system away. It can warp the very fabric of space around it, and release more energy in 1/10 of a second than our sun will produce in its entire lifetime. Scientists call it a magnetar, the most terrifying object in the universe. And the scariest part, there is absolutely nothing we can do about it. But to understand why this object should terrify you, you first need to understand how it comes into existence. And that story begins with the violent death of a giant. Deep in space, massive stars burn through their fuel at an unstoppable rate. When a star at least 10 times the mass of our sun finally runs out of energy, it doesn't just fade away. It collapses. In a fraction of a second, the entire core of the star crashes inward. The outer layers are blasted into space in a supernova, one of the most violent events in the universe. But what happens to the core itself is where things get truly unimaginable. All that mass, billions of tons of matter, is crushed down into a sphere only about 12 miles wide. Think about that. A star heavier than our sun, compressed into something smaller than a city. The matter is so tightly packed that a single teaspoon of it would weigh around 10 million tons. This is called a neutron star. And most neutron stars are already extreme. But a small fraction of them, maybe 1 in 10, are born spinning incredibly fast, with magnetic fields trillions of times stronger than Earth's. These are not regular neutron stars anymore. These are magnetars, the most magnetic objects in the known universe. And their magnetic fields don't just sit there quietly. They twist. They strain. They build up pressure, like a coiled spring waiting to snap. And when they do snap, the consequences are catastrophic. But before we see what happens when a magnetar breaks, you need to understand just how extreme its numbers really are. Because once you hear them, you will never look at the night sky the same way again. Let's start with the magnetic field. Earth's magnetic field protects us from solar radiation. It is what makes compasses work. It is relatively weak. A magnetar's magnetic field is approximately 1 quadrillion times stronger than Earth's. That is a 1, followed by 15 zeros. To put that in perspective, if you took a regular refrigerator magnet and scaled it up to the strength of a magnetar, it would be powerful enough to pull the iron out of your blood from halfway across the planet. Now let's talk about density. We already mentioned that a teaspoon of magnetar material weighs about 10 million tons. But let's make that real. 10 million tons is roughly the weight of all the steel in the entire Golden Gate Bridge, compressed into something you could hold in your hand. If you could somehow drop a single teaspoon of this material onto Earth, it would punch straight through the crust and keep falling until it reached the center of the planet. Now let's talk about gravity. On the surface of a magnetar, you would weigh about 100 billion times more than you do on Earth. If you weighed 150 pounds here, on a magnetar, you would weigh 15 trillion pounds. Your body would be crushed instantly into a thin layer of atoms. And finally, the temperature. A magnetar's surface can reach over 1,000,000 degrees Fahrenheit. That is roughly 200 times hotter than the surface of our sun. All of this, packed into an object smaller than New York City. But extreme numbers are one thing. Watching what a magnetar actually does is something else entirely. And on December 27, 2004, humanity got its first real glimpse. 50,000 light-years away from Earth, in a constellation called Sagittarius, a magnetar named SGR 1806-20 was about to do something no one had ever seen before. The magnetic field of this magnetar had been building up stress for years. The crust of the star, made of solid neutron matter, was literally cracking under the pressure. Then, at 21:30 and 26 seconds Universal Time Coordinated, it snapped. A starquake. The star's crust fractured, releasing a burst of energy so intense that it briefly outshined every other object in the universe. A wall of gamma rays and X-rays, moving at the speed of light, shot out into space. It traveled silently, invisibly, for 50,000 years. And then, it hit Earth. But here is the terrifying part. Because the burst came from outside our solar system, we had no warning. No telescope detected it in time. No alarm went off. For all intents and purposes, it just arrived. The radiation slammed into Earth's upper atmosphere, and actually physically changed it. The ionosphere was ionized so violently that it briefly expanded. Satellites were overloaded. Some were temporarily blinded. Instruments on spacecraft across the solar system, from Mars orbiters to probes near Saturn, all registered the hit. And this was from 50,000 light-years away. If the same magnetar had been just 10 light-years from us, the radiation would have stripped away our ozone layer. Life on Earth's surface would have ended, and we wouldn't have seen it coming. So we got lucky. 50,000 light-years was just far enough. But what if it wasn't? What if a magnetar was closer? Let's run a thought experiment. Imagine a magnetar slowly drifting toward our solar system. At a distance of 1 light-year, we would barely notice it. Maybe a slight disturbance in cosmic rays. Nothing dangerous. But as it gets closer, things change fast. At 1,000 astronomical units, roughly 10 times farther than Neptune, the magnetar's magnetic field would begin interfering with the sun's own magnetic field. Solar flares would become unpredictable. Earth's magnetosphere would start to warp. Satellite communications would degrade. At 100 astronomical units, roughly inside the Kuiper belt, the tidal forces from the magnetar would start disturbing comets and asteroids. Some of them would be flung toward the inner solar system. We would face an increased risk of impacts. At 10 astronomical units, roughly the orbit of Saturn, the magnetar's gravity would begin visibly disrupting planetary orbits. The gas giants would shift. Saturn's rings could be torn apart, and Earth's climate would start becoming unstable. But the real nightmare begins at 1 astronomical unit, the distance from the Sun to the Earth. If a magnetar replaced our Sun, every planet in the solar system would be torn to pieces. Earth wouldn't just be destroyed. It would be spaghettified, stretched and compressed by tidal forces until it was nothing more than a stream of superheated plasma. And if a starquake happened at this distance, the resulting gamma ray burst would vaporize everything in its path. No warning. No escape. Just silence. Now you might be thinking, this is just a thought experiment. Magnetars aren't actually near us, right? Here is the truth. We don't know exactly where every magnetar is. We have only confirmed about 30 of them in the entire Milky Way. But astronomers estimate that there could be hundreds, possibly thousands, drifting through our galaxy right now. Most of them are far away. Most of them will never affect us. But here is what keeps scientists awake at night. A Magnetar's most violent outbursts. The Starquakes are completely unpredictable. They don't follow a schedule. They don't give warning signs. One moment the star is quiet. The next moment, it releases energy equivalent to a supernova. In less than a second. And because gamma rays travel at the speed of light, by the time we detect the burst, it has already hit us. There is no defense. There is no shelter. There is no time to react. We would never see it coming. We would never know what happened. 1 second. Everything is normal. The next. It's over. We spend so much time worrying about asteroids. About solar flares. About black holes. But the real cosmic threat is a dead star smaller than a city, with a magnetic field that defies comprehension. It is out there right now. Silent. Invisible. Waiting. We just have to hope that when it finally snaps, it is not pointing at us. Because in the end, that is all we can do. Hope.